Thank you. The provenance of our data matters. In 2009, a leak of thousands of emails exchanged between climate research scientists called into question the validity of their results, leaving them scrambling to refute the accusations of skeptics. A year later, this seemingly benign Lady Gaga CD passed through a military checkpoint. Unbeknownst to the guards stationed at that checkpoint, the CD had just been used to exfiltrate thousands of classified documents. More recently, lab technicians in Massachusetts were arrested for tampering with court-ordered drug tests. In the aftermath, the lab couldn't even say with certainty which tests had been accessed by these technicians, calling into question tens of thousands of drug-related convictions. Now, in all of these cases, a lack of data provenance led to disaster. What those climate scientists needed was a description of their data that explained the series of analyses they performed to lead to a particular conclusion. What that checkpoint needed was a monitoring system that tracked the flow of transient data through the base. And the drug laboratory needed detailed documentation of every lab test workflow so they could precisely identify which results may have been corrupted by those technicians. Provenance matters because it provides all of these things. Now, unfortunately, another common link between each of these scenarios is that they reside in malicious environments. The trustworthiness of the scientist, the whistleblower, and the lab tech are all in question. So if provenance had been available, these agents may have been strongly incentivized to tamper with that provenance trail in order to hide evidence of their misdeeds. In light of this knowledge, it quickly becomes apparent that it's only valuable when we're confident of its integrity, authenticity, and completeness. Up to now, though, little attention's been paid to the design of secure and resilient provenance collection mechanisms. Now, we tackled this challenge in this work, creating a secure provenance-aware system. We present Linux Provenance Modules, or LPM, a kernel patch that provides a provenance monitor for the Linux kernel. LPM introduces a provenance layer to the operating system that permits the observation of all system events related to the manipulation of kernel objects. Rather than introduce redundant protections, we demonstrate that LPM can be secured using the existing Linux security mechanisms. To further motivate the capabilities of our system, we go on to present a scheme for provenance-based data loss prevention. In contrast to existing enterprise solutions, which are often based on heuristic and error-prone primitives, our DLP mechanism is able to make enforcement decisions based on the true flow of information through the system, offering dramatic improvement over the state of the art. With LPM, provenance has not only been made easy, it's also cheap. We show that our system imposes as little as 3% overtime, computational overhead, on realistic workloads, and that our data loss prevention mechanism can search complex ancestries for system objects in just a handful of milliseconds. The rest of the talk is going to be structured as follows. First, I'll give you a brief primer on provenance, followed by the design and deployment of LPM. I'll then introduce our data loss prevention mechanism, describe our evaluation results, and conclude. So data provenance is metadata that describes the history of an object that's been processed on a computer system. This history details what's happened to the object from the time it was created, including how it came to exist in its present state. Provenance can be expressed as a graph in which nodes are users, data objects, and processes, while edges convey relations between these nodes. So on the provenance graph here, we see that there's been an output that was generated by a process, and that process used two inputs in order to create it. Meanwhile, that process was controlled by a particular user. So given its value, in this work we assume that provenance is a ripe candidate for attack. To conceptualize this, we introduce a provenance-aware adversary. Now, a provenance-aware adversary is just one that recognizes that provenance is being collected on the system. So they might take any number of actions, including attempting to disable our provenance collection mechanism, avoiding taking certain actions on the system in order to remain invisible to the provenance monitor, or they might set out to corrupt or falsify the provenance that's already been collected. We make the following assumptions in the design of our system. We considered all user space applications to be potentially subject to compromise and therefore potentially untrustworthy. Once compromised, an application might begin to emit false provenance that lies about its actions on the system. We also considered the kernel to be vulnerable to runtime compromises, although we assumed that the kernel as distributed and installed was in a known good configuration. Finally, we assume the presence of some public key infrastructure that is going to assist us in allowing provenance-aware hosts to be able to communicate. Since we want provenance that's comprehensive enough to reflect any possible action taken by an attacker, it's necessary to explicitly define what type of provenance we're trying to collect. To do so, we define whole system provenance as the complete and exhaustive description of how agents have controlled activities in order to manipulate controlled data types during system execution. Now, the significance of this definition is that controlled data types are a concept from the Linux security literature. They enumerate all of the kernel objects that inform the system security state. So if we capture provenance for all interactions with these objects, we should have complete visibility into the actions of the attacker on the system. So with this in mind, we set out to design a system that possessed the following security properties. First, that our provenance mechanism satisfied the reference monitor concept, that it have complete observation of all system events, that it be tamper-proof, and that these properties were verifiable. Beyond the reference monitor guarantees, our system needed to facilitate the deployment of distributed provenance-aware systems, providing a channel that assured the authenticity and integrity of provenance that was transmitted over an untrusted network. A final consideration to our design was that of provenance layering. So in order to bridge the semantic gap that exists between the operating system and application workflows, we can create provenance-aware applications that voluntarily disclose information about their activities. However, in our threat model, we assume that any application is potentially under the control of the attacker. So our system must offer a gateway that can upgrade disclosed provenance to a high integrity state. To describe LPM, I'm going to be iteratively introducing system components to this diagram over here on the right. The foundation of LPM is currently shown on the screen. A set of hooks are placed around the kernel. They're registered by a provenance module, and that module subsequently generates provenance and transmits it to user space for storage. LPM instruments the kernel with 170 dedicated provenance hooks. Unlike the Linux security module's authorization hooks, provenance hooks are not intended to mediate access or alter the control path of the function in any way, but instead to passively observe system activity. The flowchart on the left depicts how provenance hooks affect the open system call. When a process in user space attempts to open a document, it's first going to go through a series of error checks and discretionary access control checks, followed by the Linux security module authorization hook. If there's an LSM enabled and this activity has been approved, then the provenance hook is reached. LPM examines the context and creates a new provenance record. Now, with a provenance hook, LPM actually has the ability to deny access to a request. However, in practice, this only happens in the event that LPM fails to allocate memory to create a new provenance record, at which point it needs to deny the activity. By mirroring these Linux security module authorization hooks, the provenance hooks are able to observe all security-sensitive operations to control data types. This includes things like operations on files, sockets, shared memory, interprocess communication, and basically all of the major operating system primitives you can think of. So through surveying the provenance literature, it quickly became apparent to us that researchers have dramatically different needs from provenance. So this motivated the modular design of our system. LPM currently offers support for the Hi-Fi system, which was originally based on an LSM module, the SPADE scientific auditing project. LPM has also been used by researchers in the Uptempo project, which seeks to use provenance to perform automatic generation of mandatory access control policies. Now, when provenance events are generated in the kernel, they're immediately transmitted to user space for storage. This provenance recorder interprets the kernel stream and records the provenance into one of a number of different storage backends. We offer support for writing to compressed binary files with the gzip library, relational databases with PostgreSQL, NoSQL databases with Neo4j, and also an in-memory graph database that makes use of the Snap graphing library. When considering distributed environments, it's necessary for each network message to be associated with a unique identifier. This is going to allow the recipient of a message to later recover provenance from the sender of the message. However, if we're going over an untrusted network, there might be an attacker there that could strip or modify that provenance identifier. So to address this problem, LPM also registers a set of net filter hooks, which it uses to implement a message commitment protocol that resides entirely in the kernel. For each outbound packet, LPM signs over the immutable fields of that IP packet header, as well as its contents, and then embeds the signature into the options field of the IP header. When the packet's received, LPM first verifies the signature. If the signature verification fails, LPM can be optionally configured to drop the packet. This is so that the provenance record remains a complete and total reflection of the events that happened on the system. So a flowchart of this message transmission sequence is shown above. LPM's the last kernel component to modify the packet prior to its transmission, and the first kernel component to handle the packet upon reception. At no time can user space processes view or modify the contents of this IP options fields, nor can they circumvent our net filter mechanism. So in this way, our message commitment protocol is both mandatory and invisible to user space, ensuring its compatibility with all applications. Another important consideration in the design of LPM is that of layered provenance. Capturing provenance at the kernel layer offers all of these wonderful properties, foremost among them being its completeness. It gives us a total view of system activity. Now, unfortunately, the kernel is unable to understand the internal semantics of individual applications, leading to a need for layered provenance architectures. However, since our threat model assumes that user space applications are prone to compromise, how can we trust the provenance that they disclose? To preserve our security goals, we need a means of evaluating the integrity of provenance-aware applications. Our solution is to turn to the Linux Integrity Measurement Architecture, or EMA. EMA computes a cryptographic hash of each binary before its execution and extends this measurement into a register in the system's trusted platform module, at which point it publishes the measurement to kernel memory. So when an application wishes to disclose provenance, it first contacts the provenance recorder. The recorder looks up the process ID of the sender, which it uses to check the EMA measurement against a list of known good configurations. Hence, if a binary had been modified by the adversary in order to emit false provenance information, this activity would be detected and the provenance would be rejected. This provides an assurance that layered provenance remains in a high integrity level. We consider the following secure deployment of LPM in our security analysis. Using the Trusted Platform module, we ensure the platform integrity of LPM using an Intel Trusted Boot sequence. Trusted Boot measures each system component before loading it, preventing attackers from being able to force a reboot into a different kernel. The Trusted Platform module is also used to prove to remote hosts that LPM's in a known good configuration. Once the correct kernel is loaded, we need to preserve its runtime integrity. Now for this, we turn to SE-Linux. We make use of the SE-Linux MLS policy and write some small policy modules to protect all of the user space components that are introduced by LPM. Our arguments for the security of this deployment are as follows. For completeness, LPM's provenance hooks are a superset of the LSM authorization hooks, with each authorization hook in the kernel being immediately followed by a provenance hook. The placement of the LSM authorization hooks have been repeatedly validated through both static and dynamic analysis techniques, notably through the efforts of Edwards, Jaeger, and Zhang, concluding that there is an authorization hook on the control path of every sensitive kernel operation that manipulates a controlled data type. Therefore, since the provenance hooks have mirrored the authorization hooks, LPM offers the ability to record complete provenance for those same operations. For tamper-proofness, LPM's runtime integrity is assured through the SE-Linux MLS policy. In particular, SE-Linux is there to protect the trusted computing base of the kernel and also of LPM's user space applications. An attacker can't reboot into another kernel due to the presence of trusted boot technologies. One of the most viable attacks is that of a resource exhaustion attack. DOS the system until there's no more room to collect provenance. However, LPM can deny system activities in the event that it's unable to allocate new memory for provenance. So for as long as the system is usable, the provenance record remains complete. LPM's hook placement inherits the formally verified properties of the LSM authorization hook project, as well as the runtime integrity assurances of past work with analysis of the SE-Linux MLS policy. However, the verification of individual provenance modules is not addressed in our work, so we leave that to future work. Our message commitment protocol, which is implemented entirely in the kernel, provides an authenticated channel between provenance-aware hosts. Applications running on either host are unable to interfere with this protocol because it occurs immediately prior to transmission and immediately upon packet reception. And because LPM suppresses applications' ability to access the get and set IP options system calls. An adversary in the network cannot tamper with a message or else the signature won't verify, at which point the message won't be delivered to the application. Our secure disclosure mechanism provides assurance that provenance-aware applications are in a known good configuration at the time that they're loaded. Unfortunately, it doesn't address the possibility of a long-running program being compromised during execution. Runtime integrity attestation is what we need for that, and that's a challenging problem that was simply outside of the scope of this work. All right, so next I'm going to further motivate our system by telling you about a data loss prevention tool that we built using LPM. Data loss prevention is monitoring software that seeks to minimize the spread of sensitive data in large, complex organizations. However, current enterprise software often makes use of heuristic approaches that aren't rooted in the true flow of information through the system. We address this by creating a new provenance-based data loss prevention primitive. The tool was comprised of both a monitoring and enforcement phase. In the monitoring phase, an administrator is able to reason about the flow of information on an existing system. For example, if a database on the system contains sensitive client information, they could search the system for all objects that were derived from that database. Using this information, the administrator can create an informed policy about which objects are not allowed to leave the system. We implemented an enforcement phase as a file transfer mechanism that's shown here on the screen. Now, prior to permitting a file to leave the system, this application is going to scan the provenance of that file. If one of the ancestors of this file matches the policy, then the transfer of this file is going to be blocked. By surveying publicly available white papers describing existing DLP products, we conducted an informal analysis that compared our provenance-based primitive with existing approaches. Most DLP systems make use of regular expressions to recognize data. The major problem with this, of course, is that it can't handle any sort of data transformation, right? You know, if I have a credit card number and I encrypt it or I compress it, then it's no longer going to look like a credit card number. Some DLP tools, in contrast, make use of security labels, but rather than use system layer labels like we might be familiar with, they do this entirely in user space and do this by manually annotating the metadata of Office documents. So I might have Microsoft Office with a plugin that allows me to select a security label for a new file that I created. So because these labels are manually annotated, it's unlikely that they're going to be able to provide complete enforcement of any policy. And they might especially struggle in the case where we have data fusions in which a new file is derived from multiple previous files with differing security labels. Now, in contrast, our provenance-based mechanism follows the actual flow of data through the system. So in our case, we're undeterred by data transformations and data fusions because at all times we maintain a complete record of the true ancestry of every object. To gain a better sense of the performance costs of collecting provenance with LPM, we ran a series of benchmark workloads. The first was the classic kernel compilation macro benchmark, in which we saw that provenance collection imposed 2.7% performance overhead compared to compilation on a vanilla kernel. We next ran the BLAST genomics benchmarks, which are simulating typical biological sequencing workloads as published by the National Institute of Health. Here we observe 4.8% overhead. Finally, we ran the postmark tool, which simulates an I/O workload for an email server. Here we observe 7.5% overhead, and the reason for this increase is due to the manner in which the Linux kernel, and particularly LPM, perceives file I/O. So if we're opening a file in a nested directory, there's actually going to be an access check for every single directory in that path. So when that occurs, rather than create a single new provenance event, we actually create multiple provenance events. This is in contrast to other system calls where there might only be a single new provenance record created for a particular event. Hence, I/O-intensive workloads are going to experience slightly higher overheads. Now, a major challenge to performing automated provenance collection, which is what we're trying to do here, is the high storage overhead incurred. So to capture that, we performed the kernel compilation benchmark again and plotted the growth of our provenance storage using different recorders. So this top line here is the raw volume of data that was generated by the kernel, which was about 4.5 gigabytes of raw provenance in only 10 minutes. Now, fortunately, this only required 450 megabytes of storage using our compressed recorder, but provenance in this format couldn't be efficiently queried, so we also turned to our in-memory graph recorder in the middle there. Since this was an in-memory graph, we estimated the amount of storage required by polling the procfs system, and we found that it required approximately 1.6 gigabytes to store this in-memory graph. Now, these results merely serve to show that provenance storage overheads are a major consideration, and that incidentally, these overheads are roughly consistent with past work in developing provenance-aware systems. It's just that those past systems haven't had all of these wonderful security guarantees to go along with. These overheads could be managed through compression and garbage collecting techniques that have been proposed elsewhere in the literature. Now, in a second series of tests, we attempted to characterize the query performance of the provenance we collect with LPM. We did so using our data loss prevention tool. First, we built a provenance graph by replaying the log from the kernel compilation trial. Uncompressed, this log was 4.8 gigabytes in size. The resulting snap graph contained roughly 6.5 million nodes. So for every data object in this graph, we then issued a query that traversed the object's complete ancestry, its total history, and then returned that to us. To keep short-lived objects that didn't have many ancestors from favorably skewing our results, we ignored responses from data objects that had less than 50 ancestors. So the cumulative density function for that is shown here. For 98% of the objects in this graph, the query returned in just about 2.5 milliseconds. In the worst case, which was a data object with 17,700 ancestors, which, since it was the kernel compilation trial, was the kernel itself, that returned in just 21 milliseconds. So this is really exciting because it's an indication that we can do real-time or nearly real-time analyses of provenance even when we have these huge graphs. Finally, we benchmarked the performance of our message commitment protocol using iPerf. Unfortunately, we found that our DSA signing scheme resulted in dramatically reduced throughput, which naturally follows due to the fact that we were doing a DSA signature for every single packet. We considered the possibility of using batch signatures to reduce this burden, and we did find that that significantly improved throughput. At the end of the day, this message commitment protocol is a strong tool for providing network integrity for data provenance in transit, and in some environments, it might impose an acceptable cost. Other possibilities that we did consider would be the use of IPsec or symmetric signatures to speed things up. I'll refer you to the paper for our rationale for why we chose to go with this approach. To wrap things up, in this work, we've identified the requirements for trustworthy provenance in distributed and complex computing environments. We present the design, implementation, and deployment of the world's first fully realized provenance monitor. That is a provenance collection mechanism that provides reference monitor guarantees. And we go a step further by showing that provenance can be used to improve the state of the art in data loss prevention software. If the things I've been talking about today excite you, our source code is currently available at linuxprovenance.org. We have a copy of our kernel on Red Hat. We'll shortly be releasing a copy of our kernel for the mainline Linux kernel. And we also have all of our user space recorders and storage and software there. With that, thanks so much for your time this morning. I'd be happy to take your questions now.
Great. If you do have questions, please do come up to the mic, state your name and your affiliation.
Yusheng Sun from Penn State. So I have a question. So you said the completeness of these provenance hooks are guaranteed by Linux security module, since every provenance hook follows a LSM hook, right? So do you find the case that you actually need more provenance hooks than LSM hooks?
We actually did, and this was something that was identified by some previous work by Devin Poley et al. called the Hi-Fi system. They found in particular that one difference between the security hooks and the provenance hooks were that they were interested in the ordering of packets received, and that actually couldn't be done using the existing hooks. So they introduced a couple of new security hooks to the networking stack in their work, and we mirrored them into our work. So there's some cases where the context of provenance is slightly different than what the security system needs.
Okay, so but other than that, you could directly use LSM hooks for provenance? Yeah,
and I think that this would be a wonderful time to move to one of my backup slides. So one of the main reasons that we initially chose to use a dedicated system over instrumenting our own provenance hooks rather than using the existing Linux security module architecture was due to the fact that stacking of modules was not natively supported. Like, you needed to use a community patch in order to provide that. We were concerned about going that route because we didn't know what it meant to have multiple modules, multiple reference monitors enabled on a system at the same time. That could potentially lead to unpredicted behavior. Now, just this summer, there's been a push to the mainline kernel to enable support for security module stacking. So we're currently investigating using that in place of the provenance hooks that we've instrumented, because at the end of the day, that would provide easier usability for the system that we're working on.
Okay, thanks.
Hi, Stefan Suri, Microsoft Research. Great work. I really loved it. I have some clarification questions. So I'm trying to understand, what is the identity of an object in the provenance data? How do you identify an object there?
So the main primitive that we're tracking is kernel forks. So we'd expect, every single process is going to be associated with, particularly a kernel credential, but not every kernel credential is associated with the process. So every single time there's a fork in the kernel, we assign that a new provenance ID and then collect, the user that was in control of that provenance ID, the binaries that were launched, and the files that were read and written.
And how do you prevent a rollback attack where an attacker would replace the provenance data with older provenance data?
So we configured an SELinux policy module for that provenance recorder that I showed on the screen, and our storage basically saying that there was only one party that could read the kernel stream from user space. There was only one party that could write to storage. So we we've isolated our provenance computing base from the rest of the system.
I see. Okay. Thanks.
Thank you.
Hi, Nicholas Carlini, UC Berkeley. What do you do about side channels?
Yeah, that's a very fair question. We don't have a solution for side channels. We're not alone in that, okay. Right? So one thing that we did think about, and we discussed it in the paper, is things like the copy and paste buffer is a pretty big side channel, right? That is something that could be singularly addressed.
Even worse, I'm thinking timing issues. Cache timings, especially, because those seem very, very hard to do anything about.
Yeah, certainly. So that was sort of out of scope. We did think about, we're concerned with semantic information that we're losing by being in the operating system. So we did think about, can we have a provenance-aware X windowing system, right? And then we'd have some of these other things. But no, like hardware-level side channels, we don't address in this work.
Thank you.
Thank you.
Great. Let's thank our speaker one more time.
Thanks, guys.